This is solving simple circuits using stepwise reduction. That's what the process is called.
Who do you want to call?
Nobody. Ghostbusters. Samantha, can you check and make sure that's in focus and that those circles are, like, back it up just a little bit so the circles are like taking up as much screen as possible? You can do it. I believe in you. Come on. Back more. Back more. All right, that'll have to do. Is it in focus? Is it? Yeah. Okay, I can't tell it on my glasses on. Okay, so before we go on, we did talk about something yesterday, and you're going to need that for today. So what you need is to remember that there are series and parallel elements. We need that for today. A series element is when I have resistors that are like in a row, like so. They are in series. So R1, R2, R3. If I want to replace those three resistors with one resistor that would be equivalent, then if you remember from yesterday, for series, the equivalent resistance is just the sum. It's pretty straightforward. Add them all together. Now, yesterday we got to a point where there was a parallel element. You remember? And it was not obvious what was going on there. You remember that too? Today we're going to kind of show what happened there. When they're in parallel, we're like adding more lanes of traffic. So we should expect the resistance to go down. How it goes down, though, might not be obvious. When you have a parallel element, to find the equivalent resistance, what you have to do is a little more complicated. It's not as obvious what you're going to have to do. To get the equivalent resistance, you have to add the inverses and then invert. What I mean by that is the equivalent resistance is the sum of the inverses. But that's not equal to the equivalent. It's equal to the inverse of the equivalent. That's the formula. Let's demonstrate how this might work, okay? First, let's just say that R1 was 6, R2 is 3, and R3 is, 4. Just making up some numbers. If they were all in series, it'd be 6 plus 4 plus 3. Right, it'd be 13. That's not a big deal. If, however, they were in parallel. Parallel is a little different. Let's say R1 is 6, R2 is 3. The equivalent for this circuit is 2. Because to get the equivalence, it's 1 over 6 plus 1 over 3. By the way, that is not 2/9. I'm saying that because there's people out in the room who think it's 2/9. Or there's people who, in a fit of stress on their test or next quiz, will write this down as 2/9. And although you're shaking your heads no now, I've been doing this for 23 years, and there's always somebody in every class who doesn't know how to add fractions. I promise when I get that quiz, it'll be up on the bulletin board for all of us to see. I post one a year for 23 years. So don't let it be you. I promise to redact the name, maybe, but not the handwriting. Do we have an understanding? You got to add fractions together, and I'm probably not going to have a whole lot of patience for you if you can't. Common denominator is the rule, so this will be 1/6 plus 2/6, which when I add them together is not 3/12, but 3/6, because I remember how to add fractions. But the answer isn't 1/2, and that's the other mistake you'll make, and that's a more difficult mistake, because this is not equal r, this equals 1 over r, which means 1 over r equals 1/2, so r equals 2. You understand? It is the sum of the inverses and then inverted. You will always come out with a resistance that is less than either of the resistors that are in parallel. Always. Okay? Now, tuck that away for a minute. You're going to need access to it, but those are actually on the equation sheet. So, yep.
Right. So if you have two.
Ultimately, our goal is to transform this one circuit with lots of resistors down to a single resistance. That is called stepwise reduction. Now, when we're done with this, the whole board is going to be filled with numbers and stuff. So instead of what I would normally do, which is just talk at you, what I want you to understand is we are going to spend a few minutes just laying out a map of reducing our circuit one set of elements at a time. You see, we can only reduce our circuit if we see something in the circuit that strictly matches the definition of series or strictly matches the definition of parallel. Currently, I've got things there that look like they're in series and parallel and series and all sorts of stuff. So we can only reduce something that looks specifically like series or specifically like parallel. In fact, I only see one thing that we could actually reduce right now, and that's these two. They are in the strict definition of series. So I'm going to start a road map, and I'm going to draw one of these arrows with a little squiggle in it to indicate that I am reducing the circuit. I'm going to make it smaller. And I'm only going to be dealing with this portion of the circuit, the part from here to here. So I'm not going to draw a complete circuit. I'm just going to draw the resistor portions of the circuit. But I'm going to draw a new circuit here where I have replaced the series portion with a single resistance. Meaning the 4 is still here, the 3 is still here, but I'm going to replace those two that are in series with one that is in parallel. I'm sorry, with one resistor, not one in parallel, just one resistor. Now, like I said, I'm going to lay out a roadmap of what I'm going to do, so I'm not actually going to do it yet. I'm just kind of making a roadmap of how I'm going to reduce my circuit, one step at a time. So when I have reduced that one piece down, I'll notice that my new circuit has a clear example of a parallel element in it. It doesn't include that 4 ohm resistor at the top, but it will take away that parallel element with the 3 ohm in it. So my next step will be some circuit that looks something like that. And then my last step will be a final circuit with one resistor where I take those two that are in series and reduce it down. This is my roadmap for reducing my circuit. All right? So we are still on phase 1, which is reducing my circuit. Now, making a mistake in reduction, you understand, is probably going to blow the whole works. Because once I introduce a mistake, everything will be based on that mistake from there on out. So I want to be careful and apply the rules carefully. But this one's pretty easy. It's going to be 4 plus 2. I think we can handle that, can't we? 4 plus 2 is going to be 6. So 6 ohm right there. That's my first stepwise reduction. Good so far? I'm going to go to my next reduction. I have those two that are in parallel. Now, we just did this exact parallel as an example a moment ago, so I don't think I have to write it all out. Are you good with that? I have a 6 and a 3 that are in parallel, so it's the whole 1 over 3 plus 1 over 6 thing. And we know that that's going to equal what? Yeah, 2 ohms, because we just did that one. But I would use the rules for parallel for that. And for our viewers watching at home, just a reminder that that's how I got it. Of course, now I have 2 resistors that are in series. I'm just going to add them together. That'll give me my 6 ohms here. So basically, I could take this entire circuit away and replace it with one equivalent resistance of 6 ohms. And the battery would be none the wiser. This is phase 1. Reduce your circuit down to a simple circuit with one resistance. When you're done, what you really have is an 18-volt battery connected to a 6 ohm resistor. Phase 2 begins at the end of your reduction and works backwards. In phase 2, we are going to attempt to find the voltage and the current for each circuit element. Generally, we're going to use Ohm's law and Kirchhoff's rules. But we're not going to use the Kirchhoff's rules you learned. We're just going to use the implications. So I'm going to start by recognizing that I have the voltage, but not the current. So usually, step 1 involves Ohm's law. For this particular case, I have 18 volts and a resistance of 6 ohms. Using Ohm's law, that suggests 3 amps. Right? 18 divided by 6, 3 amps. Now, when you have found the voltage and the current for a particular step, you're going to then step backwards through your circuit. When you step back, you have to decide how your circuit changes. For example, in this instance, I'm going back to a set that's in series. Series elements have the same current passing through them. So when I step back to series, I take with me the current. And I apply the current to all the elements that are in series. Okay? Any question about that? Notice I applied 3 amps to each of the elements in series, because objects in series have the same current passing through them. Now, my next job is to use Ohm's law. I have to find the voltage and current at every step. This is a step. So I'm going to use a different order of Ohm's law, but that's not a different equation. I'm just going to take 2 times 3 and get 6 volts, and 3 times 4 and get 12 volts. Now look, stop here for a minute. Every step gives you a chance to check your work. There was 18 volts there before. Do I have 18 volts now? 12 and 6, yes I do. You get these wrong, it's because you want to. There's always a way to check your work. I would encourage you to make sure you stop and check your work. Now I'm going to point out something, that this will begin to happen when you do these, that you're going to have a resistor that doesn't change when you go back a step. Right? This 4 ohm resistor is this 4 ohm resistor right here. I don't have to do anything to it. It's 12 volts and it's 3 amps. In fact, it's 12 volts here and 3 amps here. That resistor is the same resistor all the way back to my original circuit. So that one's done. However, the 2 ohm resistor isn't really a 2 ohm resistor, is it? It's 2 resistors in parallel, a 6 and a 3. So when I take the current back to a set in series, what do you think I take back to a set that's in parallel? What do you think? If series gets current, what is the likely alternative for parallel? Voltage, yeah. Because we just said in class about 30 minutes ago that if you have a junction, all the segments of a junction have the same voltage. So when I step back to a set that's in parallel, I'm going to take the voltage and apply it to all the elements that are in parallel, because parallel takes the voltage. There's only voltage and current. We had the resistance. So when I step back, parallel takes the voltage. You apply the voltage to all of the segments of your parallel element. They all see the same voltage. Once I do that, Ohm's law again. 6 divided by 3, 2 amps. 6 divided by 6, 1 amp. I'm going to point out there was 3 amps before. 2 plus 1 equals 3. You make an arithmetic mistake, you should be able to catch it. And that's how you do it. You check to make sure. I only got one step left. Going back to the original circuit now. That 3 ohm resistor doesn't change, so I'm just going to write in at 6 volts and at 2 amps. Unfortunately, the 6 ohm resistor wasn't a 6 ohm resistor at all, was it? It was a 4 ohm and a 2 ohm, and they are in series. So what do I take back with me? That's right. So there's 1 amp. I apply my 1 amp there and my 1 amp there. 1 times 2 is 2 volts. 1 times 4 is 4 volts. 4 volts and 2 volts is 6 volts. All right, I told you when we're done, you're just going to see nothing but a mess on the board. And I wasn't wrong, was I? It's a mess. Now, I hope your notes tell you a few things. Maybe a few more things. Stepwise reduction is 2 phases. Phase 1, reduce your circuit to a single resistance. Use the rules of series and parallel. Phase 2, starting at the simple circuit, work backwards, applying rules for series and rules for parallel, with series getting the current and parallel getting the voltage. By the way, some of you probably recognize that this was one of the quiz questions. Please take a look. This was the 18-volt quiz question. I just laid it out differently. How do you think I figure out what all those voltages and currents are? So,